So hopefully we all know that the area of a 2D sphere is pi r squared, and the volume of a 3D sphere is 4 thirds pi r cubed, and the volume of a 4D sphere is... Wait, what? In this video we're gonna derive the volume of this thing, and the derivation requires like just a little bit of calculus. And of course I can't really teach, like every calculus topic to understand like the what do you call it? Like the technical parts of this video. So a background in at least Calc 2 is recommended, but you can just watch. Alright, so first I need to clarify some stuff. So firstly, we need to think of an n-dimensional sphere as an infinite collection of varying sizes of n-1 dimensional spheres stacked on top of each other through the direction of the nth dimension. For example, a 3D sphere is just a bunch of circles just stacked on top of one another. This is actually really easy to show in Desmos. We can see that this sphere is just comprised of a bunch of circles, just like this. So in a way, a 4D sphere is just a bunch of 3D spheres stacked in the fourth dimension. Next, if you don't know the slicing method for finding volumes, I'm going to teach you real quick. Now, if you already know slicing, just skip this. So let's say you have some function f. This looks real weird, but whatever. And you rotate it about the x-axis. The solid generated by rotating it about the x-axis would look something like this. Now, if we were to take a cross section of any part of this freaking solid, we would see that it is a circle, since we're just rotating this about the x-axis. And the radius of any of these circles, you can see that it would just be the function's height, or just f of x. So the area of the circle would be pi times f of x squared. The whole idea behind this is just we're getting a representative slice of this solid and then finding out its volume by first getting the area of the slice and multiplying it by its width, which would be dx. Since ideally we would do this an infinite number of times to get the actual volume. So the volume of this solid from an interval AB would be this integral down here. All I'm really doing here is just introducing the idea of cutting a solid into an infinite number of slices and then adding them all up to get the volume. The last thing I need to clarify is that the graph of, let's say, y equals 2 in 2D space is just a line, and for 3D it's a plane. So in 4D, the graph of a variable equaling a constant is just going to be a 3D space. So now, since we've clarified all that, let's start. This is the equation for a sphere centered at the origin in 3 space. And a 4D sphere lives in a system that has 4 spatial dimensions. Since we don't have any letter after z to represent the fourth one, we'll just use w or something. So this is the equation for a sphere in 4 dimensions. So the trace of this sphere in the space z equals k, we get this, which can be simplified to this if we just subtract k squared on both sides. So since r and k are both just constants, r squared minus k squared is a constant. So that means this is the equation for a sphere with this radius. Let's keep this in mind. So the volume of a sphere is 4 thirds pi r cubed. And since in our 4D sphere, this was the radius, we can say that this is the volume for the trace of our 4D sphere in the space z equals k. So since we're just adding up a bunch of these an infinite amount of times, we just need to make the volume into an integral, which is this integral right here. And if you're wondering where the negative r and r comes from, since our sphere will be centered at the origin because it doesn't really matter where it's centered at. We're gonna integrate from negative r to r, since we're just adding up a bunch of these traces from negative r to r. So since 4/3 pi is just a constant, we can just move that out of the integral. So all we need to do is just integrate this. Alright, so first we need the antiderivative of this. To expand this, we're just gonna rewrite it as this. And you'll notice that this integral has this root, this style, which means we can do trigonometric substitution to solve this integral. So I've constructed a quick right triangle here to do this. So we see that sine theta is k over r. So k is just r sine theta. And then if we differentiate this, we get dk d theta is r cos theta. So we get dk is r cos theta d theta. And we see that cos theta is the root over r. So the root is equal to r cos theta. So going back to our original indefinite integral and making these substitutions, mainly these two, we get this integral right here. And since r to the fourth is just a constant, we can just move that out of the integral to get this. Now we just need to find the integral of cos theta to the fourth, or cos to the fourth of theta, whatever. And there's actually a formula for the antiderivative of cos x raised to the nth power, which is this right here. Making the substitution n equals 4, we get this. And now there's also an integral here, so we'll just use the same formula for this integral right here. Using this formula again for this integral, we get this. And here we have cos to the 0 of theta d theta, and anything to the 0th power is just 1, so this is just the integral of d theta, which is just theta. Simplifying all of this, we get this. So now this is the antiderivative of cos to the 4th of theta d theta. Going back to this triangle, we know that cos theta is this and sine theta is this. But what is just theta? Well, since sine theta is just k over r, if we take the arcsine of both sides, we get theta is arcsine k over r. So we can substitute that for theta here. What is this, bro? And since before we had the integral simplified to r to the 4th times the integral of cos to the 4th of theta d theta, which is this, we'll just multiply this by r to the 4th and substitute these in for, and we get this, which simplifies to this. And if we distribute the r to the 4th, we get this whole thing. So originally we had this integral, and then the antiderivative of this turned out to be this. So we'll just make a substitution now. So now we have 4/3 pi times this evaluation from negative r to r. You'll notice that if you plug in r or negative r into k, into these two first terms of this evaluation, all the roots come out to 0. So this is something times 0. So these first two fractions are just going to simplify to 0. So we'll just simplify this evaluation to only include the last term, which is this. So first let's plug in r for k. So here we get arcsine, if you plug in r, we get arcsine r over r, which is just arcsine 1. And since sine pi on 2 is 1, that means arcsine 1 is pi on 2. So the first part of the evaluation is this, which simplifies to this. So now we need to subtract this evaluated at negative r. Substituting that for k, we get arcsine negative r over r, or arcsine negative 1. Now you might want to say arcsine negative 1 is 3 pi on 2. And that would kind of make sense since sine 3 pi on 2 is negative 1, but that's actually incorrect because the range of the arcsine function is from negative pi on 2 to pi on 2. So the next best option would be negative pi on 2. So now we get this, and this means to add them. Simplifying this, we get this, so now we just need to multiply this stuff, which gets us this. If we simplify this, we're gonna get the volume of a 4D sphere, which is this. Oh yeah. So now, if we travel to the fourth dimension and we want to find volume of a 4D sphere, here we have it, radius r. When I first derived this like yesterday, I was actually like quite proud of myself because I hadn't known there was a formula for the volume of an n-dimensional sphere, which is this. So you can actually use this method of slicing to find the volumes of like fifth dimensional spheres or seventh dimensional spheres, or even like a million dimensional spheres or something. But if you wanted to do this for the millionth dimensional sphere, you would obviously need to do this a million times, which is not ideal. Or you could just, use the formula, I guess. Alright, bye.